Hi everyone, today we will continue with chapter 4. Our topic is imperfections in solids. So here I have atomic arrangement for crystalline solid. So far we assume that crystalline solids are perfect, but actually we have some defects, such as one of these atoms may be missing. It should be there, but it's not. It's empty. So today we will cover this kind of defects and we'll analyze how this defect can change material properties. And you have to keep in mind that these defects are not a bad thing, not at all. If you had perfect materials, it would be difficult to deform materials, to give shape to materials. But let's see in details. So first we will start with point defects. So here, as you can see in this picture, we have this perfect arrangement, crystalline solid. So here, this time we will have some vacancy. That means some of these atoms will be missing, such as this one. So the atom which should be here is missing. So as a result, atoms around it will try to fill that space. As a result, this plane, as you can see, instead of a straight line, it is distorted. You can see the shape over here. Let me change the color. So instead of the straight line, this plane is distorted, and others also. Those atoms around it will be under tension. They will try to get away from each other and fill that empty space. So it's called vacancy defect. And here we have subinterstitial. As you can see, I have this perfect arrangement. This time I will have extra atom in that interstitial spaces, such as this one over here. So this one should not be here, but we have subinterstitial, so this atom is here. So as a result, it will push other atoms aside. It will compress them aside. So atoms around it will be under compression. So I have two: vacancy, where I have missing atom, and subinterstitial, where I have extra atom at interstitial place. And as a result, in both cases, the planes are distorted, bent. This kind of point defect is impurity. So impurity means we have more than one element in structure. We are able to purify materials until that point, so we never have pure material. So here I have given you structure of nickel, but it has got some missing atoms. We have vacant spaces over there. So when we have vacant space and we have some other element which is similar to this metal, so in this case, these gray ones are nickel, and copper is very similar to nickel. That's why copper will substitute nickel and fill that space, that vacant spaces. So here, we call this kind of thing substitutional solid solution. The copper substitutes nickel, fills that vacant spaces. And what is solid solution? If copper is distributed uniformly in nickel, we call this solid solution. If it is not distributed uniformly, it will create a new phase. So here we are talking about solid solution. And here in solid solution, we have a solvent, in this case nickel, and we have solute, copper. The solvent I have in greatest amount, and solute will be least amount. Let's say I have a nickel, and copper dissolves in nickel. Nickel is solvent, copper is solute. And another name for solvent is host material. Here nickel is host material. Now on the left, I had substitution salt solution where copper fills vacant spaces. So here, on the right, I don't have any vacant space, but I have this interstitial spaces in between, let's say here, iron atoms. And what will happen, a carbon, which is really small, can go interstitial spaces in iron and create interstitial solid solution. So carbon atoms, which is too small, is uniformly distributed in iron structure and goes into these interstitial spaces. And by using this phenomenon, we can give some more strength to iron. So we have substitution salt solution and interstitial salt solution. Let's continue. In order for elements to create substitutional salt solution, we have some rules. For example, in order to copper to dissolve in nickel, copper should comply with 4 rules. The first, atomic radius difference between two elements should be less than positive or negative 15%. They should have similar electronegativities. In periodic table, when elements are close to each other, they have similar electronegativities. That means they will create salt solution. If they have a large difference in electronegativity, they will, let's say one will be more electropositive, one will be more electronegative. So large difference in electronegativity means one of them will be wanting more electrons, another one will want to give electrons. As a result, they may form some ionic bond and create a new compound. But if they have similar electronegativity, this will not happen and they will create solution. So our rule is similar electronegativity, that's why they will not form new compound. The third one, they should have same crystal structure. If one is FCC, another one should also be FCC in order to dissolve completely. And the last one is valency. Their valency should be equal, or if one of the elements has got large valency, it will have more tendency to dissolve in host material compared with an element having lower valency. Let's see this one over here. Here I have some elements are given. Most of it are metals. Atomic radius, crystal structure, electronegativity, and valence are also given. And the question is to find which one, if zinc or aluminum, will dissolve more in copper. In this one, I will do some. I will do this one on Excel and try to find for all elements which ones will form which kind of solution in copper. So let's see. Here I have copied information from table to this one over here. Here copper is our host element, solvent. Let's differentiate it. Now this one. So first I will calculate difference in radius between copper and other elements. So I will have radius of radius of copper minus radius of carbon and divide it by radius of copper. Gives me percentage because I have chosen this percentage sign beforehand from here. So I will do this all for all those elements. So each time radius of copper minus radius of element over radius of copper. In order to do that, I will press F4 for this one. So I don't want equation change copper value in equation. So now I can drag it. As you can see, each time, if you see this power here, C3 didn't change. Now from here we can see that These ones are outside of range. It is more than negative or positive 15%, but these ones are in range. Let me do this. For second one, crystal structure. Copper has FCC, so others which has FCC crystal structure has a chance to dissolve completely in copper if other conditions are met also. Now for electronegativity, let me find difference in electronegativity again. I will press F4 again for copper value. I don't want equation to change for copper. So again, aluminum minus copper, cobalt minus copper, and etc. So you can see silver has got the same electronegativity with copper, but I will keep it to last. Now check for valency. This minus valence of copper, and I don't want valence of copper to change. So press F4, drag it. Now, let's see which ones has the same valence with copper. This ones. Now let's try to analyze. I will do my analysis in this order. First, radius. Let me write it here. I will first check for radius. Second, crystal structure. Third, valency, and I will look at your electronegativity. So, first, and let's see, this one has the same radius, but in between them, the ones which have FCC, let's take these ones out. They have different crystal structure from copper. Actually, let me do this. I will select all of it, and okay, this one has the same radius, but inside chrome, cobalt, iron, and zinc has different crystal structure. Let's take them out. Now I am left with this ones. I've applied radius and crystal structure criteria. Now let's move on to valency. Cobalt has the same valency, but it's out. It has got different crystal structure. Iron is out. Nickel and this one has the same radius and similar radius and the same crystal structure. I will keep this one, and zinc has the same valence, but it has got different crystal structure and it's also out. What I'm left with, I have silver and aluminum, but these two has different valences, so these ones are also out. So what I'm left with, these three has similar radius, similar crystal structure, same valency. Let's look at your electronegativity. Difference in electronegativity is 0.1, 0.0, and 0.3, which is not so great. So these three elements will create complete solid solution with copper. Okay. So these three. For partial solid solution, let's look at again. From argentinium to zinc, all had same radius, but some of them had a different crystal structure. Some of them had different valency. So these ones will create partial solid solution. So again, first rule, check radius. So this ones has a chance to create substitution solid solution, but because of some differences in crystal structure and valency, so this will be these ones will create partial solid solution because of minor differences with copper. So I am left with carbon, hydrogen, and oxygen. As you can see, their radiuses are greatly different, 44, 64, 53%. These ones will create interstitial solid solution with copper. So that is it. If you return to our question, it was asking which one, zinc or aluminum, has a high chance to dissolve in copper. Let's see. zinc or aluminum. Aluminum has a similar radius, same crystal structure. Zinc has similar radius but completely different crystal structure. That's why aluminum has more chance to dissolve in copper because this crystal structure is important too. So let's return. Our answer for this one is aluminum. Let's continue. When we talked about impurity, we had more than one element, so we have to specify amount of each element. For example, if you are mixing carbon with iron, we have to specify how much carbon is inside iron. We can tell this by grams, but to make things easier, we will find some percentage. So if I'm using mass, weight, this is what we call the weight percentage. So I will take amount of carbon divided by total mixture and multiplied by 100%, it will be 10%. So this one, I can note it like this. Carbon will be 10 weight percent and iron will be 90 weight percent. So it's also called composition, that is amount of carbon in weight percent, or we can solve this one with atom percent. If we know number of moles in certain mass of carbon and number of moles in certain mass of iron, let's say, we can calculate atom percent. The value will be different from weight percent. And in order to find it, if you know the mass of carbon, which was 100 grams, and atomic weight, we can read this one from periodic table. For carbon, if I remember correctly, it was this. And divide it, find number of moles for carbon, and do the same for iron, replace and find atom percent. Mainly we will be using weight percent, but sometimes maybe in some articles you will come across with atom percent, or even you will see some volume percent. In book, Materials Science and Engineering in Callister, William Callister's book, you will see equation for volume percent. I will not be using this one, that's why I will skip it. And also, we can transform from weight percent to atom percent and do the reverse. As you see this equation, if you plug in this equation over here and do the same for this one, you can simplify and get this same equation above. So it's a simple one. Let's continue. Before we have talked about point defects, but here we will start with linear defects. Linear defects. We call linear defects dislocations. So dislocations are linear defects. It has got two kinds. One of them is edge dislocation, and it looks like this. If you see this one here, as you can see, I can trace some line. Let me change the color. I can trace this line over here, this full line, and this is for others. But here it is half line. So I have this one extra, half extra of line of atoms. It's called edge dislocation, and that's the sign for it. So here, this, if you say this one, this points towards dislocation line. And where is the dislocation line in this picture? If you see this half extra atom over here, the last line, which will be this. First, if you see this circles behind it, or look at this here, if you can count atoms, so this one has another atom behind and another behind, so it is a line of atoms. I have the same thing over here. All this line of atoms here will be dislocation line. So end of this half plane is the dislocation line, and this T points toward it. I can have something else. Draw something like this. So here, that's my half extra plane, so dislocation sign will be like this. Again, this 2 points show vast dislocation line. In this case, will be this atom and another atom with the same line. So that line comes out of the page. Plus, if you see this Burgos vector over here, which is denoted by B, it has got some direction and magnitude. It shows amount of dislocation, magnitude and direction of dislocation. Here, in this case, magnitude of dislocation is 1 unit cell length. If you see this length here, so this unit cell length is my magnitude for Burgos vector, and direction here, as you see it here. So where is my dislocation line? It is comes outside of page here. This dislocation line and Burgos vector will be perpendicular in H dislocation. And if you want to know why this length is 1 unit cell length, it is amount of dislocation. If you see, let's do something like this. First, I will erase all ink on the slide. In order to find magnitude of Burgos vector, we will do this. I will start from here. I will move 1 over here. 1. I will move up. 1, 2, 3. 1, 2, 3. 1, 2, 3. And if you see, I have this open space over here. I can join this because this half is missing. And how I can join this one? In order to join this, I can draw this kind of vector. This was start. And this one is finish. I will connect start with finish. That's it. And that is Burgos vector magnitude and direction. So we are connecting, we are tracing a line. So I moved 1, 3 up, 3 left, 3 down. And here I need to move 3 in total, but I can't because I have missing atoms over here because it's H dislocation. And I'm connecting start with finish and I get some vector. That vector is Burgos vector. And that vector's length will show how much dislocation has moved and the direction of it. Let's continue. Second kind of linear dislocation is screw dislocation. It gets the name from screw. As you see this side over here, it's kind of this top plane over here is kind of rotated back. It's kind of you tear this in two. If you look at from top, dark orange one will be top layer. This one is top layer. And this one is bottom layer over here. Notation for screw dislocation is this. And again, we have Burgos vector to show magnitude and direction of dislocation. In order to do this, you should apply the same notion. Let's try to do this. I will move 2 down, 1, 2, 4 left, 1, 2, 3, 4, 4 up, 1, 2, 3, 4, and 4 to the right, 2, 3, 4. I will move 2 down. As you can see, this one is not connected. In order to connect it, this is start, this is finish. I have to draw some vector from start to finish. So that is it. That is Burgos vector. As you can see, it's the same one over here. It shows direction of dislocation and magnitude of dislocation. Here I have this Burgos vector in top view. It is 1 unit cell length because top plane has shifted 1 unit cell length to the right. That's why my magnitude is 1 unit cell length. It could be bigger. Let's continue. I can have pure H, pure screw, or mixed dislocations. On the side, I have screw dislocation, and here I have a edge dislocation. And in between all these parts, you can see it on top view clearly. In this part, I will have mixed dislocation, both screw and edge dislocation. So we can have some mixed, we don't always have pure edge or pure screw. That's it. And these dislocation lines will define material properties actually. If we sum them, we have linear defects, which we call dislocations. These are one-dimensional defects or linear defects. In edge dislocation, we have extra half plane of atoms. Berger's vector was perpendicular to the dislocation line. In screw dislocation, it was kind of a shear plane in half. Berger's vector was parallel to the dislocation line, where Berger's vector itself measures magnitude and direction of distortion, or measure of lattice distortion. These are the same thing. We can see these dark lines are dislocation lines, which is seen on the microscope. The line defects. These line defects or dislocations helps in deformation. When you deform a material, that deformation takes place on that deformation lines. We will see this in detail further in chapter 7. But for now, let's do some introduction. So here we have sink bar. It is before deformation, it is after deformation. What has happened? This deformation takes place over here because I had some dislocation lines over here. It was a deformation was possible, and you can see the same real picture over here. That is single crystal, and you can see this planes all are parallel. On that planes we have directions, and that plane and direction defines where deformation will take place. So as you can see here, slip here is for deformation. Slip between crystal planes result when dislocations move. The dislocation, that defect lines move, planes move. As a result, we have permanent plastic deformation. That's why we are learning that dislocation lines. So let's see here. I have drawn two FCC crystal structure. Both are FCC, but I have drawn two different planes. This one, which plane is this? This one is one plane. More likely one plane. Yes, it is one plane, and this one is 0 plane. If you calculate planar density for these two, you will see that planar density of 1 plane will be larger than planar density of this plane. That means 1 plane is full with atoms. These atoms are closely packed to each other. That's why the planes which have high planar density, we call them close packed planes. The atoms are close to each other, less distance between them. But here, the case is different. Atoms are far apart from each other, less densely packed. On that planes, we will have some directions. Let's say direction 1, and I will take this direction over here. This direction will be 1, -1, 0, 1 direction. And for this one, it will be -1, 0, 0 direction. Again, if you calculate linear density for this direction, you will see that the -1, 0, 1 will have larger linear density compared to -1, 0, 0 direction. That means this direction over here the atoms on that direction will be close to each other, packed closely, more atoms on that line. And again, we call that kind of directions close packed directions. So we have close packed planes, close packed directions where atoms are close to each other. And why we are talking about this one? When deformations happen, it happens on close packed planes and directions. And why? In order to deform material, we should apply some stress. Let's say I have 3 atoms on that line. In order to move this atom, let's say I have to apply stress 3 magnitude. In order to move second atom, I need to apply stress 9 magnitude. And in order to move this last one, I need to apply stress, let's say 81 magnitude. The amount of stress required to move each step of atom is increasing exponentially. And if these atoms are close to each other, I will need less stress. The closer the atom, less stress is required. That's why if I choose close packed planes and directions where atoms are close to each other, that means distance will be smaller. They are close to each other. So that's why it's preferred for deformation. Let's take what will be a difference in between these 2 atoms. If the side is A, that difference between 2 atoms will be A under square root of 2. For this one over here, the difference between 2 atoms is A. So that's, see, this value is smaller. So these atoms are close to each other. You will require less stress to move this one. So if you're applying stress 40 megapascal, the element has several planes. So on this plane, because these 2 atoms are close to each other, it will be easier to move them. So 111 plane, negative 101 direction will move first under this stress value because easier to move them. And this one will be waiting until all these close packed planes and directions are used for deformation. I will clean all this stuff. So here what we have. In FCC crystal structure, we have a lot of planes and directions with high planar density, with high linear density. So a lot of close packed planes and directions to help in plastic deformation. In hexagonal close packed, we have only 1 plane and 3 directions, which is close packed, which helps us in deformation. And in body-centered crystal, we have none. And that means, let's say, more close packed plane directions, more deformation. That's why FCC crystals will deform more. HCP will deform, let's say, medium, and BCC will deform less. What will happen? BCC materials will be brittle, and FCC materials will be ductile. If you look at this picture, we have magnesium, which is HCP, and aluminium, which is FCC. These 2 specimens had the same shape before deformation. After we apply tensile stress to both of them, what has happened? Because aluminium is FCC, it can use close packed planes and directions to deform. So material deforms to prevent fracture. Instead of fracturing, it deforms and keeps together. So here, this shape, so it goes and gets thinner and thinner. That means it deformed, large deformation. And after it was at its critical point, it fractured in middle. So aluminium, FCC, it deforms before fracture. But for HCP, again we have deformation. This shape means it deformed to some amount, but it didn't deform as much as aluminium because it doesn't have so much plane and directions to help, close packed plane and direction to help in deformation. And for some materials, you can see that it fractured like this. No deformation. It can't deform because it doesn't have close packed plane directions. It just fractures. So that's it. That's why we learn crystal directions, crystal structures, and planes to understand and to manipulate and use brittleness, ductility, and plastic deformation of materials. Let's continue. We have talked about linear defects so far, point defects. And now we will see solidification process. So imagine this white background is liquid and this black dot is solids. As temperature drops, liquid transforms into solid. And how does it happen? This, if you see this solid nucleus, this will start to grow. How? This liquid atoms over here will join this solid. The liquid atoms over here will join this solid. So as time goes by, these solids will grow until they meet each other. So here you see this grains has grown and now they can't grow anymore. They have met each other, they just stuck. These are grains, and this grain which I have drawn over here are grain boundaries. And why I'm talking about this one, because these are imperfection itself. These are area imperfection. Let's see in atomic scale. So here, this first, I have 1 grain, 2 and 3 grains represented in this picture. And what has happened here? Let's analyze orientation. Here, this atom's orientation comes this way, afterward change to this because the grains where I am going over grain border. And over here, this one comes like this and change to this. I have this slight angle of misorientation. Here I have this large angle of misorientation. So this one will be called high angle grain boundary. This one below small angle grain boundary. And these are imperfection. These grain boundaries are itself imperfections because I have this continuity in orientation. These are area defects. And why these grain boundaries are important? If you see, if I pick some atom over here, this atom is surrounded by other atoms, so it has created some bonds. This atom, green atom, is satisfied because it has created sufficient amount of bonds. But if I take another atom on this border, it is surrounded on this side, but if you see this side over here is empty. It has created some, but it is far away bond. So it's not satisfied. It has got some energy to bond to some elements, to go into chemical reaction with another element. So I can say the same thing for all atoms around grain boundaries. So atoms on grain boundaries are chemically active. They have higher energy than atoms inside grain. That's why grain boundaries has higher energy compared with grains itself. That's why if I apply some chemical on it, grain boundaries will dissolve first. The high energy, they go into chemical reaction first. And after grains themselves go into chemical reaction. And we use this kind of phenomenon to analyze phases, grains, and grain boundaries in polycrystalline materials. To summarize, so far we have talked about point defects, which is vacancy defects, interstitial defects. We have impurity, substitutional salt solution, and one more, interstitial. All these are point defects. We had line defects, which we call dislocation. We had 2 kinds, H dislocation and screw dislocation. And by the way, I forgot something on screw dislocation. Let me go back. In screw dislocation, where is our dislocation line? So this tearing. This shear ends here. If you just draw this line over here, that is dislocation line for screw dislocation, and Burgos vector is parallel to screw dislocation line. Now let's return back. So we have our line defects, and the last one is area defects, which we talked about grain boundaries. As you see, this grains cover some area. That's why it's two-dimensional defect, and line are one-dimensional defects. We have some other kind of area defects, but I will not talk about this one, only grain boundaries. Let's move on. We use microscopy to analyze materials, grains, specific grain size, grain boundaries, and phases on grains. We do this, for example, we may have some heat treatment on a material, and we check with microscopes that if we have done heat treatment properly, or we can measure some grain sizes to define material properties, because grain size defines material properties such as hardness, ductility, strength, and etc. Or let's say some material has fractured in some component of a ship or airplane, and etc. And we can analyze on the microscope why did it fracture. If you look on the microscope, we can analyze the source of fracture. So let's move on. With optical microscopy, we can magnify up to 2,000 times, and that's enough to analyze grain size and boundaries and phases. What we do first, we get our specimen and polish it until it's mirror-like. Then, if we have our specimen, we apply some chemical to it. That chemical we call etchant, and that process is called etching process. What has happened? This etchant goes in the chemical reaction with our element, and we have certain different class of etchants for different elements. For example, for iron carbon, we use certain one. For copper alloy, we use another one. So whichever is suitable for ours, for our element. So after we apply etchant, that etchant goes into chemical reaction and views each grain, dissolves each grain at different proportion. Why? If you look at this picture over here, these blue lines are orientations of grains. If you see, each one has different orientations. That's why each grain will be dissolved in chemical at different rate. Let's say this one will be dissolved more, this one will be dissolved less, and etc. That's why each grain will have different height measured from microscope. So what will happen? Because they dissolve in different manner, they will reflect light in different manner. If you see, this one comes this way and returns this way. You see, comes, returns this way. This one comes this way and is reflected in another way. The different reflections will be perceived by microscope, and microscope will give us different color for different or different reflections of light. And underneath you can see this, some grains are shown as dark black, other one is gray or white, because these are because of different reflections by grains. And that, as a result, we can analyze grain size, phases, and etc. And by the way, we use different kind of etchants to reveal different phases, and we will talk about phases in details in further classes. Let's continue. So again, we have element. This one is grain boundary. Before we apply chemical, that's our grain boundary. After we apply chemical, because this grain boundary is chemically active compared with grain itself, what will happen? This grain will be dissolved first, dissolved more compared with grain. So as a result, now that new shape of this element will be something like this. Now the groove, we will create a groove over here, this side is dissolved, not there anymore. So this grain boundaries will be deeper and reflect light in different manner. As a result, on the microscope, because it is deeper and this one is more shallow, the grain will be lighter color on the microscope, and this grain boundaries will be darker color on the microscope. As you can see here, these grain boundaries are black lines because all these are grooves. So all these are grooves. When I mean groove, I mean this thing over here. As a result, we see a dark black color. The one of the important thing is to determine grain size. Why we try to measure grain size? When I first look at this picture, you see this, I can have some grains which is bigger or smaller. So when we have large grain, this kind of element over here will be more ductile. It will be less strong compared with this one over here. This kind of grain will be less ductile and more strong. And by manipulating grain size, we can change material properties. We want material which is strong, doesn't deform easily, or sometimes we need material to be more ductile, to be able to deform a little bit more. Because if material doesn't deform, it breaks catastrophically. And that's why we try to change these values as required from us, let's say. And that's why we have to measure grain size to define these properties to see if I have done it properly or not. Let's say. So here, as you can see, these numbers are given 1, 2, 3, 4 all over this. These are grain size numbers defined by American Society for Testing and Materials. Grain size change between 1 and 10. 1 means I have large grain in size. 10 means I have small grains, but more of it. I have more number of grains, but sizes are smaller. If you see here, when grain size is 1, how many grains can you count? 1, 2, 3, 4, 5, 6, 7, and etc. But these are large grains, but 7 in total. But here at 8, I have maybe thousands of grains, but each one is smaller. That's why when grain size, grain number goes higher, that means grain size goes smaller. So here we have an equation. N is number of grains. This small n is grain size number. So how do we calculate it? We have space. I will draw 2 rectangles. Each one is 1 inch squared. Let's say if grain size number is 2, it will be this minus 1, 3. That means in 1 inch square I have 3 grains. If grain size is 4, I'll have 15 grains in the same area. Let's say something like this. So as you can see, smaller value, smaller grain size means large grain, and larger grain size number means small grains in large quantity. So as a summary, we have talked about point, line, and area defects, and told that these defects are not bad thing, not at all. It helps in mechanical deformation and in other properties. For example, in point defects, you have vacancy defect. Let's take vacancy defect as a point defect. We can add, let's say, if I want to make a material electrically conductive, I can add some other element which is electrically conductive to the previous one and increase its conductivity. Or Let's say I can add carbon to iron. It will be interstitial solution, and I can increase strength of iron, but it will be more brittle as I add carbon, but more stronger. Let's say stronger. It will be stronger. As a result, we are manipulating properties. And again, in line defects, we may have some edge dislocations or skew dislocations. But I know that these dislocations helps in plastic deformation. If I want my material to be strong and not to deform, for example, imagine, let's do this. Just imagine you have a building, and that building is supported by pillars. Would you like these pillars to deform under the weight? If these pillars deform, let's say it's catastrophic, the building will collapse. In this case, you don't want your building to deform. For an example, for another case, you have a phone, let's say an iPhone. You would like your phone to deform and not to return to its previous shape when you carry it in your back pocket. So in this case, you don't want it to deform. So how you can do this one? By getting rid of that dislocation lines. The less dislocation line, more strength. And on the other side, you don't want to be more strong. If you have very strong material, it doesn't deform, not at all. This time, when you carry your iPhone in your back pocket, it will just fracture instead of deforming. So you want deformation, but in less amount, and we can control it if you know dislocation lines and how to play with them. So we can calculate, we can change amount of defects actually by controlling temperature. If I have high temperature, these electrons will get more energy to move, to break bonds and move away, and that, as a result, we will have more vacancy defects. And we have talked how these defects affect material properties. And these defects may be desired or not desired. It changes according to application. So next, and that's it. Thanks.